MASA as it exists now was created to solve one problem. So the basic problem, most of my career has been in Swiss type screw machining, and Swiss type machines are very specialized, and they're unique in that they're highly optimized to make high precision small parts out of a wide variety of materials, any kind of metal or even plastics. You know, they were originally perfected for the Swiss watch industry. All the tiny little parts that go on Swiss watches are made on Swiss type screw machines. That's why we call them that in the US.
Yeah, they're not called Swiss machines in Switzerland, are they?
No, they're called sliding headstock.
Yeah.
It's just like they don't call Swiss cheese in Switzerland. They don't call French fries in France. You know, this is all American stuff. So they're sliding head machines, sliding headstock machines is basically, or the French word is décolletage, which means bar machines, automated bar machines. Because the raw material is a bar of material. Mm-hmm. So you'll get steel, titanium, plastic, aluminum, brass, bronze, whatever, copper in a bar shape, mm-hmm. and then that's automatically fed while the machine does the work on the part.
You ever do it with wood, like super hard Brazilian, like rosewood or anything like that?
You know, I don't know that ever wood is. I mean, I'm sure it's been tried. It's probably been done before. Somebody's made bar stock out of wood. But because the parts tend to be so small and wood grain is larger, wooden parts are generally bigger, right?
Yeah.
You don't usually make real tiny parts out of wood just because you're getting close to the cellular size of wood. Yeah. And, the grain is too big and all that. You know, the Swiss type machine, it's a very powerful niche. It's for the type of products that they make, there's no other way to do it productively. It's a very specialized part of machining in general. The way Swiss machines are made, there's the bar stock. So on the front end of the part, you're holding onto a bar. It's very easy because it's a long cylindrical piece. And then you machine the part at the end of that bar. And then you have to cut it off. So there's a sub spindle that comes up, grabs the part, and you cut it off. And then it comes over, and it's like another machine inside of the machine, and you can do machining on the back side of the part while the front side's being made. So when the Swiss type machines were first made, to be accurate, collets are tapered metal sleeves that you pull into a taper and they collapse. They're super rigid. That's why they're more rigid than a jaw chuck. They're more rigid than any kind of clamp or anything. It's the most rigid way to hold a small part accurately, because it's like surrounded by solid steel, and then these three tapered wedges come together and just clamp on it. It's like the part's wrapped in solid steel. It's very important to hold parts rigidly when you're doing machine work on them, because it takes a lot of force to cut metal, right? So you really have to hold the part rigidly. When it's attached to the bar, it's easy to hold it rigidly, because you can have a big old chuck here and hold it, and then do machining, and the bars provides the holding surface. When you're machining the other end, it's a much more delicate part, because the part can look like any shape, like dental implants have little fragile threads on the outside, or bone screws, or electrical connectors have thin walls, and there's all sorts of medical device components, mm-hmm. or little tiny screws like for your eyeglasses and stuff. Those little threads are real fragile. Mm-hmm. So to machine the back end of the part, it's a much more intricate clamping problem. But when they first invented these machines, they came up with what they call the dead length collet. The collet doesn't move to close. The sleeve pushes over the collet to force it closed. So they put the same collet system in the main system as the sub spindle. So even though the work holding problem is a lot different in the sub spindle, it's the same. Even to this day, they use the same collets in the main as in the sub of even current day machines. Now, when a sub spindle comes up to the main spindle, there's two big spindles that come up next to each other, and then your tool has to get between it. So clearance is really important. So on the sub spindle, what they do is they take a conventional collet, and then they put an extended nose on it. So it's an extended nose collet. So the collet closes and the part can be, so it gives you a little gap. So when the sub spindle comes up, you have a space between the main and the sub. So it's a tapered space, and your tool can fit down between there to do the cutoff operation. And that's a big theme in Swiss type machines is tool clearance. That's one big advantage they have over other machines is they're situated in a way so that the tools are much bigger than the parts. Parts are tiny, the tools are big, 4 inches long shank or whatever, and the part might be the size of a grain of rice or something.
Yeah.
So getting the tools into the part is a tricky proposition. That's really up until the MASA microconic system, the only adaptation they really had for the subspindle was to make an extended nose collet so it sticks out and you have more clearance for your tool. But there's all sorts of problems with extended nose collets. They're weaker, they're not as rigid, they're not as accurate because you're clamping back here and your part's out here and any error gets telescoped out. Another problem on the subspindle is because it's the shape of whatever the part is, which could look like anything, any weird screw or any weird shape. On the bar, it's easy, it's always a cylinder. On the other end, it's whatever the part looks like, which could be anything. So the collets, there's tons of specials. The collets always have to be special to be able to hold these parts. Very few standard collets in the subspindle. For one thing, because they're an extended nose, that makes them special. So for a long time in the industry, to run a part complete in the subspindle, you had to order a special extended nose collet, which may take anywhere from 2 weeks at the minimum to more like 4 to 6 weeks typically to get it. So MASA was basically created to solve this one problem of this subspindle work holding. So our system, it has a built-in extended nose. It has a rigid extended nose. It's not 3 collet tines sticking out. It's a solid, rigid, hardened steel sleeve. And then inside is our microconic collets. We just solved that one problem of subspindle work holding. It has applications everywhere. Some people use it in the main spindle for various reasons. And it can be used in other machines to optimize for small parts work holding. We also were able to, by carefully engineering the collet design, able to create an overgrip collet. Usually collets with the tapered, the typical collet doesn't open very much. It just opens enough to get the part in and then clamps down on it. Overgripping allows the collet to open way wide, reach over a larger diameter, and then clamp on a smaller diameter. Other companies have tried to do that with the push-type collet system, but because of the frictional forces in the way a push-type collet works, there's a physical limit to how steep the taper is that you can get it to open and close. So you're very limited in how much it opens and closes. Our system kind of takes away that limitation. So we open like double what anything else out there is. So it gives you a lot more advantages, a lot more capability to reach over. So this gives you the option to decide when you're running a part. You don't have to run always the smallest end out and you're just stuck running it that way. Sometimes it's more advantageous to turn the part around to either make use of other capabilities on the subspindle or to balance out operations. So when you're running a Swiss type machine, the subspindle, 80% of the time is just sitting there waiting for the main spindle. You do most of the work on the main spindle. A lot of the times, the reason for that is because you can't hold it in the subspindle to do much work. So with our system, it gives you more capability to hold it in the subspindle. You can do a lot more operations in the sub. So you can balance operations. So instead of spending 80% of the time with this spindle just sitting there doing nothing, you can shift operations from the main spindle, which reduces its cycle time, and add it to the subspindle in what they call shaded time. You're doing half the work here instead of all the work here, so it cuts your cycle time in half. So that's kind of the significance of this one niche problem that we solve. So we've really focused on that niche problem. How do you hold parts in the subspindle? I wanted to make it standardized. I wanted to make it super accurate. I wanted to make it very versatile. These are all things that were lacking and are lacking in traditional collets for the subspindle. They aren't very well standardized. They're very minimal overgrip capability. They aren't very versatile for a lot of reasons. They don't have a lot of rigidity compared to a standard collet. There are accuracy problems. So all those things I wanted to address. So we basically built a company off of focusing on solving that one problem. Our whole catalog, 50 pages of it, is dedicated to a standardized range of collets that covers every size and just about every conceivable work holding situation. But that's one of the biggest advantages of our system, is how standardized it is, how you can just get a vast table of every size. It shows you all the internal dimensions of clearance. It gives the guys that are trying to figure out how do I run this, it gives them just limitless options.
Yeah.
So, and because we just focus on that, everything's in stock. We have everything. So it's not a 4 to 6 week wait. It's all here.